Welcome to the lecture on microsegregation and banding. So, the last lecture we talked about the constitutional supercooling, and we talked that how when you have the temperature gradient line. So, it has to have a slope which will ensure the planar front to move so that there is no constitutional supercooling. Whereas, if the gradient line, temperature gradient line is such that you have a region of supercooling, in that case there may be chances and there will be formation of dendritic grains. So, and again that depends upon what is the degree of supercooling. So, we talked that the ratio G by R. So, that is to be that has to be so it has to be correlated with some value accordingly, and that is delta T by dl. So, delta T is basically the freezing range, and then you have the dl, that is the coefficient of diffusion value in the liquid. So, basically it talks about those conditions, and we also saw that when you have the different conditions, then how you have initially the planar mode of solidification, then you have cellular mode of solidification, then you have the columnar dendritic mode of solidification, and then further you go to the equiax dendritic, because when the region becomes too large and it is not possible, it becomes a remote possibility for the columnar dendrites to to grow till the whole region which is supercooled. In that case, there will be chances of the formation of equiax type of dendritic grains, and so there are ways to avoid, certainly based on the temperature gradient which you can put in. You can say that you can avoid the formation of the dendritic structures, but typically it does not happen, because having that gradient is practically not possible. So, you are bound to get that dendritic type of structure. However, certainly you can control the arm width or the dendritic arm spacing, so by certain external factors, and that is maybe the cooling rate or so. So, we had seen for example, suppose if you look at the conditions, like say if you have if you go for an example of aluminum 4% copper for this. Now, for this as we have seen that your slope of the tangent on that liquidus line, that was delta T upon dl by r, and basically that G, that is your temperature gradient. So, its value has to be more than or so or less than, depending upon the conditions will vary. So, for suppose if you take the aluminum 4% copper and its values if you take, so for them the TL that value is suppose say 650 degree centigrade, and TS is say 580 degree centigrade, and your DL, its diffusional coefficient in the liquid, it is say 3 into 10 raised to the power minus 5 centimeter square per second. Suppose that is the case. Now, in this case if your temperature gradient, so if suppose the temperature gradient G, if temperature gradient G, and this its value is suppose 700 degree centigrade per centimeter. So, as we know that G by R value, so has to be higher. So, your R value, so you can have the value of delta T. So, delta T will be something like 70 and divided by dl. So, that is how this value comes. Now, so if you get the value, now if you calculate the R, that is your growth rate. So, we have the expression like G by R. So, growth rate, that is R, that has to be less than or equal to. So, this has to be less than or equal to 3 into 10 raised to the power minus 4 centimeter per second in order to have the planar mode of solidification. And if the growth rate is higher than this, in that case the plane mode of solidification will break, and that you will be likely to get cellular or dendritic type of solidification structure. So, this we had seen in our earlier lectures. Now, the thing is that as we know that when you have the arms being formed, now these arms are basically certainly not good in the sense that you have the chance of the liquid being trapped between the dendritic arms, and that will be certainly prone to the defects or prone to the chemical inhomogeneities as the situation may be. Again, that will be depending upon again the different cases which we have discussed, that whether you have the how your diffusion is there in solid and liquid stages, like diffusion method, there may be diffusion in total solid and total liquid case, or there may be incomplete diffusion in solid and incomplete diffusion in liquid or so. So, we have discussed about these cases. The thing is that the liquid which is trapped inside these interdendritic arms or so, now they again have to solidify. Now, in those cases they are assumed to move in a planar manner, they are in a very small domain. So, there the question of the segregation comes into picture. So, the solute redistribution during the solidification results in microsegregation across cells or the dendritic arms. So, that is basically the the result of the microsegregation, because they will be resulting across the cells or the dendritic arms. So, if you talk about the the arms, so how it looks like, you see you have the dendritic or cellular type of solidification. Say you have a cellular type of structure, or you may have the dendritic arms. So, it will be going like this. So, it goes like this. So, this is your cellular type of solidification, and this is your dendritic. Now, in this you have basically you will have the liquid which is trapped in between these arms. So, you will have the liquid here. Similarly, you may have the liquid trapped in this case. So, this case again you will have so here this is the liquid element, that is volume element which is considered, or that will be. So, this if this is your center line. So, this is your volume element. So, that is how you have the small volume element. There you have the full volume of the liquid, where you will have the experience of undercooling, and then you have the formation of dendrites. But then again here also you have the liquid, and there also the solidification has to proceed, and again because of the conditions you will have in these cases also you will have the effect of microsegregation. So, the volume element covers the region from the center line of the cell or the dendritic arms you can say, and to the boundary between the cells. So, this way these volume elements are defined. Now, within the volume element the solid liquid interface may still be planar. So, in that case although we see that the overall structure is the cellular or dendritic, but within that volume element, which is small volume element, in that the interface may still be planar depending upon the different conditions, again how that condition is existing. So, based on that there may be even the still the planar type of solidification that may proceed in these cases. Now, for these it depends upon the again the different cases, and if your cases may be that there may be no microsegregation, no segregation when you have the diffusion is complete in both solid and liquid. So, based on that basically you will have different condition. So, suppose you have we talk about a ratio for the case where k is less than 1. So, equilibrium partition ratio, if you take that to be less than 1 and because in that case the slope is less than 1, certainly slope is negative. Now, in these cases you will have no segregation if you have a complete diffusion when diffusion is complete in both solid and liquid. So, no segregation if diffusion is complete in liquid and solid. So, that way this will be the condition when there will be diffusion there will be complete diffusion in liquid as well as in the solid. And for that we have already discussed that for that the condition has to be satisfied. In that case your the diffusion coefficient multiplied by time, it has to be quite larger than the distance over which the diffusion has to take place. So, for that the condition will be dl into t has to be quite larger than L square. Similarly, ds into t and that has also to be quite larger than L square. So, this is the case when you have the case where there is complete diffusion in the solid as well as in the liquid, and in that case microsegregation profiles will be like so for these cases what will happen that you have for k equal to less than 1 values you will have this C naught value will be there altogether, that will be constant. Similarly, even for k more than 1 value also this across the profile you will have no segregation and the concentration will be same. So, if you are taking for the C naught concentration. Now, second case is that now segregation will be worst. So, if you take about the another case where you have the in solid case you have no diffusion. So, no solid diffusion and you have complete liquid diffusion. In those cases the segregation that will be affected. So, that will be worst in those cases. So, if you talk about the case when you have limited liquid diffusion and you have no solid diffusion and no solid diffusion. So, if that is the case, now in these cases so you will have now if you talk about this case, that is limited liquid diffusion and no solid diffusion, in that case what happens that your this segregation profile for the case for less than 1, you will have this, so it will start from case C naught and then it will move like this, and then it will be from both this side you will have such profile. So, this will be your C naught. So, this will be the case of initial transients as you have seen in such cases, but as we have seen in earlier cases, now towards the middle portion you will have such kind of case. So, this is the case for no solid diffusion and limited liquid diffusion, because in the liquid also you do not have full diffusion. So, towards the end you have reach of in the higher of the value more than C naught it goes. So, in this case it is intermediate. However, if you take the case of complete liquid diffusion, and you will take suppose no diffusion in solid. So, in these cases this will be case when your for this the condition will be you have complete liquid diffusion. So, dL into T has to be more than L square, whereas no diffusion in solid. So, you will have ds into T is quite less than L square. So, in these cases the situation is very much severe, and here as you see in these cases what happens if your this is your C naught value. So, it will start from C naught K C naught, and then what happens that it will move and then it goes to a very high value. So, this way your profile moves like in the case of limited this will be the case when you have the complete liquid diffusion, whereas there is no solid diffusion. So, in those cases as you see that your concentration will be too high and then it will be going like this. So, your segregation condition will be worst in these cases when you have complete diffusion in the liquid and there is no diffusion in the solid as it appears in these cases. So, if you take the example of the aluminum copper alloys or aluminum alloys. Now, in this case as we know that in that case you see the eutectic composition also. So, for taking a eutectic phase diagram, if you if you look at, so you will have this is the eutectic composition. Now, this is your eutectic point. Now, if you see if you take any composition suppose here in such cases. Now, what is happening that if you take this as the initial melt composition, that is your C naught. So, this is C naught, and as you see that it will be touching here. So, this will be your for the the solid part which is coming out. So, so certainly this will be K C naught depending upon the value of K, that point will be K C naught, and then it will move through that. So, this is your eutectic point. Here this will be if you take this point, this is your TE. Similarly, this point where it is touching, this is the solidus line. So, this is Ts, and this temperature will be TL, and this will be Tm. So, if you look at this point, now this is your CSM. So, what we see in these cases again, what we see that the solid composition will be moving from case C naught to CSM. So, this way this solid this line is moving. So, solid composition as the temperature is dropped. So, the solid composition will certainly be moving along this line. So, it will be moving from case C naught. So, its concentration will be moving from case C naught to CSM, and that will be maximum when your this eutectic temperature is reached, that is TE. So, that way this eutectic at this point this comes as CM, and also the composition becomes C therefore. So, then after that it will be formed as the solid eutectic after this point. So, the fraction of the eutectic which can be formed that can be calculated as indicated earlier. So, that can be found. So, that will be the we are taking this as the complete diffusion in the liquid and no solid diffusion. So, you can have the for example, if you try to find, it will be Tm minus TL by Tm minus T raised to the power 1 by 1 minus K. So, this way you can have the fraction of eutectic which can be formed in such cases. Now, we will talk about the another phenomena which occurs, that is bending. Now, what happens that this solute segregation, it can also occur as a result of growth rate fluctuations caused by thermal fluctuations, and then in that case it is known as bending, because we have seen that in that expression where we have got G by R, and then on the other side you have delta T upon dL. So, in those cases R is the growth rate that becomes important even for the solute segregation. So, when it is occurring because of the result of growth rate fluctuation, in that case it is known as the bending. So, what happens that you may have a case where suddenly the growth rate is increased. So, if the growth rate is increased, then the extra amount of solute will be rejected into the liquid, because as the growth rate is increased. So, the solid which is lower in concentration of solute, so certainly it will be rejecting the solute at a larger rate. So, it will be larger amount, and so what will happen that so it will be rejected into the liquid at the solid liquid interface, and so the solute content will be rising. So, now as a result the material solidifies right after the increase in the growth rate. So, if there will be further material solidification after the increase in the growth rate, so it will have a higher solute concentration than that which has occurred before. So, you can see that there will be the difference, that difference can be seen in the term that the boundary layer will be becoming thinner in those cases. So, because the growth rate has increased. So, if the solute concentration eventually resume will be, if there is no further change taking place, then again the solute concentration will be eventually taking its steady value from there onwards. So, and then if suppose it is further decreased, so if suppose it may increase from one value to the second value, and from the second value again, so you will have the decrease in the growth rate. So, you will have the solute enriched band, solute rich band which is formed when the growth rate is formed, growth rate is increased. Similarly, when there is further decrease in the growth rate, so you have the solute depleted band formation in such cases, and eventually I mean that is what is the effect of the increase or decrease in the case of bending, when your there is increase or decrease in the growth rate, that is how it affects. So, that can be understood. Suppose if you look at the pictorial representation of these bending, so that you can understand. Suppose your when your growth rate is R1. Now, in that case your if you look at the solute concentration profile, now that we know that it moves from C naught to C naught by K. So, that way it moves, and then it goes like that. Now, suppose from R1 it is increased to R2, which is more than R1. So, in that case you will have a solute rich band ahead. So, your that profile, it will be looking like it will go from here, and then it will be coming down. So, you will have a solute rich band. So, that you will have and this will become thinner because it goes above. So, it becomes thinner in those cases, and as you see when your it is further decreased from R2 to R1. Now, in that case again it will be it will be smaller. So, it is coming like this. So, that way your you will have the solute rich band, and also you will have the solute depleted band formation in the case of the increase or decrease of the growth rate. There is also effect of on the cellular or dendritic structure, whether it will be finer or coarser. So, there is effect of cooling rate also. So, if you talk about the effect of cooling rate, so when your cooling rate will be higher, in that case your solidification time will be shorter. So, when the solidification time is shorter, in that case your cellular or dendritic so cellular or dendritic structure will become finer. So, cellular or dendritic structure becomes finer when cooling rate is high. So, basically that can be understood by looking at the dendritic arm spacing, and there has been expression for the secondary dendrite arm spacing D, and D basically is taken to be it is calculated as A into TF and raised to the power n, or it is also written as B into epsilon raised to the power minus n. So, D is the secondary dendrite arm spacing, and if you take the other time, that is TF, it is the the local solidification time, and epsilon is the cooling rate. So, epsilon is the cooling rate, and A and B are the proportionality constants. So, from here you can see that if the TF is less, in that case your dendritic secondary dendritic arm spacing will be smaller. Similarly, cooling rate becoming higher, this value will be smaller. So, that is basically this is the formula for finding the dendritic arm spacing, and it has been seen that as you increase the cooling rate, then the arm spacing that will be becoming narrower and narrower. So, that is the effect of increasing the cooling rate. So, increasing this value, or decreasing the time of solidification in such cases. So, so that is how you have to more and more analyze these situations. You can have the study of these terminologies, and you can have a concept that how this dendritic arm spacing will be varying by the change of either the cooling rate or the solidification time. So, we discussed about these issues in this lecture. We will be talking about other issues related to the solidification or epitaxial solidification and non-epitaxial growth in our coming lectures. Thank you very much.